Okay, this is a quick video about calculating the moment of inertia. It's not a video about what the moment of inertia is. It's just a pile of examples showing you how to work with it. I'll show you how to start with the one particle, and by the end of the video, hopefully you'll know how to do weird bizarro objects like this. And we will learn about voids, composites, and make extensive use of parallel axis theorem in order to finally attack this guy at the end of the video. Okay, so let's get going. This is the definition of moment of inertia. If you want to know why moment of inertia is defined that way, I've got another video on that. This video is purely calculational, but what this says is if you've got a bunch of particles, you look at how much mass each particle has, and you look at how far away that particle is from this. See this subscript A? That is the axis about which you are going to rotate the thing. And so I'm going to make three different axes. A and B look like points. They are not. They are lines that go into the page, and I made another axis C that lies along the plane of the page, just so you can understand that A and B are lines too. I just can't draw them because they go inward. If I start with A, then the first thing I do is I look at the first mass, which is 5. And 5 is on the axis. That means it's a distance of 0 from the axis. And you take that literally. You put in 0. Next, I look at the 2 kilogram mass, and that's 1 away. And you just proceed in this way. You take these instructions literally, and you add up all of these quantities. Okay, so that's A. If I go about B, then it's the exact same procedure, but of course now the distances change. Each one of these distances is root 2, and so I have root 2 squared in all of them. And then finally about C, in C, look, okay, I've got this 2 kilogram mass, that's only 1 away. The 4 kilogram mass, for example, that's 1 plus 1 away. So this is pretty straightforward. You just follow these instructions and they can give you more masses, but it just becomes more tedious, okay? So let's switch to what most people have a harder time with, which is continuous objects. And in this case, we're still doing a sum. An integral is a sum. It's just that you're doing a sum over an infinite number of pieces, and we have a special notation for that. We call it a big S. It's an integral. So we'll start with a 1D rod of mass m and length L. And let's make some axes about which we can take our moment of inertia. And what we are going to do is what I just said. We're going to pretend that instead of this being one big continuous object, it's actually a bunch of little point masses, and those point masses are what actually makes up the rod. What I'm going to do is make lots and lots of those point masses and then add them up. So what's the mass of each of these point masses? Well, this thing has a mass per unit length, and so what I say is the small amount of mass is equal to the mass per unit length times the amount of length that I have. Meanwhile, the distance from this piece to this axis I've drawn down here. That's RA. Okay, so the next thing we do is we make lots of those little pieces, and that's where our sum comes in. We're going to sum those up. So what do we have to do? We have to do an integral of r squared dm. That means we need to know what r is, and we need to know what dm is. dm we've drawn here. It's mass per unit length times length. Okay, and now this is where you might get options in the problem. You have two choices. One is a uniform mass, and the other is a non-uniform mass. And many people freak out when they see this, but the truth of the matter is the procedure is exactly the same for both. And I want to just do them side by side just so I can show you. So let's do the uniform case first. For the uniform case, I simply substitute in r squared, so that's the distance from A, which I'll just call r, and then dm, so my dm, that's just lambda dr. Lambda is the mass over the total length. Total mass over total length, I plug that in. If you do that integral, you get a 12th ml squared. Okay, now let's see what I do for the non-uniform. For the non-uniform, I do the exact same thing. I plug in r squared as I plugged in r squared over here, but instead of plugging in m over L for lambda, I plug in the equation that I'm given. And so if I do that, I plug this in, and I get 1/12 ml squared. Now I will tell you, this was a complete accident. When I made this up, I had no idea that I was going to get the result that it's the same value for both. This is, to be clear, an accident. I am not saying that it doesn't matter what the mass distribution in the rod is. I just thought it was interesting, and I decided to keep it, that if you have a rod whose mass is linearly increasing along the length of the rod, it ends up giving the exact same value as if it were uniform. Now, one interesting hiccup that I wanted to show you here is that I measured x from the left end of the rod. And this is a little awkward because I have defined my r as being measured from the center of the rod. And so I just want to take a minute to show you why the integral looks the way it does. So let me just clear this up for a second. This was my mass per unit length. And what I have is the r squared comes right back over, but I had to trade out the x. I have an x here. What does x mean? Well, x is the distance from the left end of the rod. And so what is that? That's nothing more than L over 2 plus r. And so I put in r plus L over 2 for x, and then you evaluate the integral. If I had used a different mass per unit length, I definitely would not get this. I'll leave it to you to maybe come up with a good conceptual reason for why, if the mass increases from the left end, you get the same moment of inertia as if it were uniformly distributed. Okay? For us, we're going to move on. Let's now find the moment of inertia about the left end, B. And one thing you can do is set up the exact same integral that we had before. So now it's r squared m over L. Now, what changes here? The minimum value that RB can be is 0. The maximum value that RB can be, all the way over here, is L. I just want to go back to the previous slide for a second. Maybe I glossed over this pretty quickly. I went from minus L over 2 to L over 2. And I want to emphasize this. The limits on your integrals are coordinates. They are coordinates. When you measure from the center, your leftmost coordinate is minus L over 2. Your rightmost coordinate is positive L over 2. When you are measuring from the left end, your leftmost coordinate is 0. Your rightmost coordinate is L. And so you end up with 1/3 ml squared. Okay? What about axis C? We could do the exact same procedure we just did before, and we'll have a slightly uglier integral, but instead I want to introduce the parallel axis theorem. The parallel axis theorem says if you know the moment of inertia of an object about its center of mass, so that's this guy in this case, right? The center for uniform would be in the center. If you know the moment of inertia about the center of mass, then there's this thing called parallel axis theorem, which says the moment of inertia about any axis that is, and this is key, parallel to an axis that goes through the center of mass, all you have to do is just take the total mass of the object and add the distance squared from the center. In other words, it's like you take the original center of mass and just pretend that there's a point particle located at your new distance away, and you simply add that. It's pretty nifty. I've got another video that derives this. We don't want to work on it. We don't want to deal with that here. We just want to show how it works. Okay, so I'll show you how that works. In this case, the moment of inertia about the center of mass we got in a previous slide. That's a 12th ml squared. And so what do? I take m and I multiply it by the distance from the center of mass to that point C. That's this. You can do a little bit of geometry and show that that distance is square root of 5 over 4. So if you square it, it's 5/4, and you end up with 4/3 ml squared. So what does that mean? That means that you are going to rotate the entire rod about this point right here. So the whole rod is going to make this weird kind of, each piece of the rod is going to make that weird kind of a loop. And if it does, it has more moment of inertia. It has more resistance to rotation because you're moving it farther. You're moving it farther. Okay, what else can we do? We could also use moment of inertia to find the moment of inertia at B. In other words, that's the moment of inertia at C, same as above. And we can say that the distance between B and C is L over 2. So I just ended up with L squared over 4 here. And here you get 1/3 ml squared, which of course is the same result we got earlier. So this parallel axis theorem, usually in most textbooks, they spend like 2 seconds talking about it, but it's so useful. I'm going to just crush this video using parallel axis theorem everywhere. Okay. Next thing is let's do a thin ring. So a thin ring, you might say, oh, is this a 2D? No, I say it's still a 1D shape, and I'll tell you why. I only have to specify clockwise or counterclockwise, and then I can tell you exactly where you go. In other words, you only have 1 degree of freedom here, and that's forwards or backwards. So this is still a 1D integral. And so we still need to do what we did before, which is break the ring up into little pieces, just like we did for the rod. And so here I have my little piece. dm is the mass per unit length times length. And I wrote ds there instead of a dx or a dl just to suggest to you and hopefully remind you that a little small piece of arc length is r times delta theta. And if I have an infinitesimal bit of angle and an infinitesimal bit of length, then it's simply lambda r d theta. And so if we want to add up all the pieces, we do the normal procedure. So I'm calling this point at the center A. You always need a subscript on your moment of inertia. Then we just say there's some limits. We'll talk about those in a second, times r squared dm. That's the definition. Okay, and then what are those limits and what do we do? Well, we're integrating over theta. And what does theta do? Theta goes from 0 all the way around to 2 pi. Okay, so 0 to 2 pi. And what do I have? The distance r is always the same. Every single piece of this ring is a distance big R. So I simply put in a big R squared there. As far as m over 2 pi r, that's the total mass divided by the total length, which is the circumference of the circle. And then I have my rd theta. So if you do all that, you get mr squared. It's a remarkably simple result for what you might worry might be a complicated object, but it's actually pretty easy. Okay, next, what if instead of going about the center, we wanted to go about an axis that cuts straight through this thing? So now r is not so simple. R is not fixed. In other words, this piece is a different distance away from the axis than this piece. So now we actually have to do a little bit of geometry here. And so we have the same as before. My piece of mass hasn't changed, so none of that will change. So I'll set up my integral. What I do want to do is come up with a parameterization. That's a fancy way of saying I need a formula for r in terms of theta. My mass tells me what I'm integrating over. R is a variable, and so I need to express r in terms of theta, kind of like how I expressed x in terms of r in that very first rod problem that we did. Okay, so in this case, r is r sine theta. That's just SOHCAHTOA. And now I'm in a position where I can set up my integral again. So the moment of inertia about b, this is my axis b, I'm calling it. So that's r squared, which we said was this, times dm. And then I simply plug in, and then you've got an integral to do. You can pause and do the integral carefully if you want to. You can take my word for it. It's not really, the point of this video is to show you how to set up the integrals, not really do the integrals. Okay, so now let's say that instead of wanting the moment of inertia about this axis, you want the moment of inertia about this axis. And now you can see r is going to kind of be a real pain. It's actually not that big a deal to find the new r, but I don't want to do it that way. I want to use parallel axis theorem. So that's what we're going to do. We already know the moment of inertia about an axis that goes through the center of mass of the ring. And now we are displaced a distance r, and all we're going to do is just plug and chug with parallel axis theorem. This is the result we got about the center of mass. Now all I do is add mr squared. This axis is really weird. The whole ring has to kind of come out of the page and around the whole time. It's difficult to see what the moment of inertia is going to be, but calculating it with parallel axis theorem is really straightforward. Okay, so that's application of parallel axis theorem. Again, the distance between the two axes, which are parallel, is r. And so I add the total mass m times the distance between the two axes, which is r, and you square that. Okay, now what if you have two things? You have the thin ring from before, and you choose to add a point mass to the end. In other words, this is two different objects that are welded together. So you might say, how do I account for that m? It's actually very easy. All you do is you take the moment of inertia of the ring if the mass weren't there, and the moment of inertia of the mass if the ring weren't there, and you add them together. It's a composite object. And so this is going to be a trick we're going to use over and over again for more complicated objects. We're going to say that's not one object, it's two objects, and each object on its own is easy. Or at least we know how to do it. So for the ring, we found 2 seconds ago that it was 3/2 mr squared. For a point mass, all I'm doing is applying m times r squared because it's a point mass. R in this case is 2r, and so if I square it, I get 2r squared, and okay, the result for this shape is 11/2 mr squared. It's not an important result. You don't have to memorize it or anything. I'm just showing you that if people mess with you and give you weird objects, you should break it into smaller objects. That's the plan. There's a very famous example in most physics textbooks where there's like a figure skater, and the figure skater, they're like, estimate the moment of inertia of a figure skater. And basically what you do is you say the figure skater is a bunch of cylinders with a big sphere for a head. And if you had to try to do it all in one bite, it would be difficult. But if you break it into a bunch of little cylinders and spheres, it's easy. Okay, let's go to 2D objects. This is for real a 2D object because now I can say, should I go out or should I go clockwise? Those are two independent directions. So this is a legit 2D problem. We do it the same way we did before. Those is break it up into lots of little pieces. So here's my little piece of mass dm. dm now in this case is the mass per unit area. So sigma is the mass per unit area. It's the symbol physicists use for mass per unit area times some small bit of area. And if you've had multivariable calculus, you say, okay, there's really nothing new here. I don't want to assume you've had multivariable calculus. You see this in your first physics class where you only need to know 1D calculus. So what I want to do is show you how to break this up into 1D slices so that you can still do kind of problem like this. And one thing to think about is how do you build a disk? Well, you build a disk by assembling a bunch of different rings. In other words, my mass element in this case is not going to be a point particle. It's going to be a ring, and I'm going to make ring after ring after ring, and I'm going to add up all of the rings. And in this case, what I can say is that sigma is the mass per unit area, so that's the total mass over the total area, and then that is times the bit of area, so that's length, the circumference of my ring, times width, which is the thickness of my ring. So I get dm this way, and notice I only have one variable here, dr. Okay, so my idea is that the moment of inertia of the disk is the sum of moment of inertias of rings, and we already know how to calculate the moment of inertia of a ring. So we're going to integrate the size of the rings from 0 to big R. What does that look like? This is dm times r squared. In other words, we said that the moment of inertia of a ring, we did this in a couple minutes ago, mr squared. So if you have an amount of mass dm, it's dm times r squared. And why is it r squared? Because I'm using different rings and I'm adding over all the different rings and I'm allowing this radius to change as the size of the ring changes. Anyway, if you do this, you'll end up with plugging in for dm. You'll end up with something that looks like this. And okay, at the end of the day, that integral shakes out to 1/2 mr squared. Now, if instead you wanted to do a rectangle, you're like, I don't want to do a ring. Well, fine. Then instead of using a bunch of little rings, you use a bunch of little rods, and we already have a formula for that. So I'll leave that to you to work out the details of that, but the procedure is almost exactly the same as what I did. Okay? All right. Now, what if you want to do about an axis that doesn't go through the center of the ring, but again, through the disk, but it goes like this, right? So what we're going to do is the exact same thing. We're going to take the disk as the sum over the rings. In this case, we say that about this axis B, it's the sum over all the rings for B. All I've done is swap out my formula. So we found earlier that for a ring, if the axis cuts through the ring like this, it's 1/2 mr squared. And so I just said dm because each of my rings has some small mass dm. And so if you do all that, the integral will shake out to 1/4 mr squared. What about for an axis C that's all the way at the end? Okay, hopefully now you're starting to see. All you do is just use parallel axis theorem. So I take my result from the previous part. That's an axis that goes through the center. These two are parallel to each other, separated by a distance r, and so I simply add mr squared. Okay, now this is hard. What happens if I add a void? This wrecks what I was doing before. There's no more symmetry in this problem. I have to somehow figure out a way to get the distance to exclude this from my integral. And I'll tell you that parameterizing that, it's not impossible. You probably figure it out, but it's annoying. It takes time. Instead, some genius figured out a trick for problems with voids a long time ago. They said this: a void isn't really an empty space. A void is what happens when you have some mass in a certain area, there's mass here, and you overlay negative mass on top of that small mass. So what ends up happening is the negative mass and the positive mass cancel, and it appears as if there's nothing there. If you're wondering what negative mass is, it's nothing. It's a trick. If you want, you can try and come up with some physical explanation for it, but we're going to treat it just as a trick. It is. There's no such thing as negative mass. Okay, so what we say is there has to be the same amount of mass in the negative area as in the positive area, and so we say it has the same mass per unit area, only it's negative, and the total mass is the mass per unit area times the area of the void. Okay, so what does this look like? The mass per unit area is the mass of the disk divided by the radius, the area of the disk. So we're finding sigma from the big shape. Sigma is m total over a total. And then we multiply by the area of the void, and that gives us that piece. And then what do we say? We say that the moment of inertia total is the moment of inertia. The moment of inertia total. The moment of inertia total is the moment of inertia of the void plus the moment of inertia of the disk. Okay? And in this case, we use parallel axis theorem again. Moment of inertia of the void about the CM, moment of inertia, that's my parallel axis piece, moment of inertia of the disk about the CM, and then another parallel axis piece. And we've actually already know how to do all of these. So about some weird axis through the center, it's 1/2 mr squared. And then for this guy, the big disk is separated by a total distance r. The little disk through its center is separated by some other distance, r1 plus minus r2 squared. Okay, so you have different h's. There's h of the void and h of the disk, but you're going to assemble this the same way you do before. Okay, next, a genuine 3D object. Here is a cylinder. It's not a rod. I'm actually saying that this thing has a radius now. What do we do? Well, we're going to do the exact same thing we've been doing all along. We're going to build the moment of inertia of a cylinder out of a bunch of tiny disks. You build a 3D object out of a bunch of 2D objects. So what does that look like? You have dm is now rho dv. So rho is mass per unit volume for a physicist. And so in this case, the volume of a cylinder is pi r squared L. And then in this case, we have an area, pi r squared, and some length, dx. Okay? And so if you add that all up, you end up with each disk has a moment of inertia of 1/2 dm r squared. You plug in dm. Now, you go from, say, minus, it doesn't really matter what your limits are here. You can go 0 to L. There's really no dependence in this integral at all for x. This, believe it or not, this cylinder is going to have the exact same moment of inertia of a disk. In other words, it doesn't matter how long a cylinder is. It doesn't affect the moment of inertia insofar as you account for the mass that's added by making the cylinder longer. And the reason for that is you are rotating about this axis, which has nothing to do with how long it is. So, okay, if you have more mass, then you have more to rotate, but simply making it longer doesn't make it harder to rotate because the length is not the way you're rotating it. Okay, so now let's do something harder. Now let's do it about this weird axis we've talked about before. So this goes through the center of this thing, like it has in the past. And so our strategy here is going to be the same as we had before, which is to say that we are going to find the moment of inertia of the cylinder by looking at the moment of inertia of disks. And the tool we are going to use is parallel axis theorem. So we know that the moment of inertia about the center is 1/4 mr squared. But now we are dislocated a distance h from that axis. And now here's the thing that's a little weird. As I move from disk to disk, the value of h changes. And so now I'm just calling this parameter dh, so some distance along the h-axis. And so now I have to integrate over that. This is my parallel axis theorem term, and it is the thing that we are going to integrate over now, okay? So I'm going to integrate. If I plug in for dm, I'll end up with something that has to do with dh. Again, I'm going to go from minus L over 2 to L over 2 because I'm calling this h equals 0. This is the coordinate h equals minus L over 2. This is the coordinate h equals plus L over 2. Okay. And then, well, the integral shakes out to something like this. It's kind of interesting. There's a piece that looks as if it's a 1D rod, and there's a piece that looks as if it is a disk. And apparently, you can just add those two together, which is a really interesting result. Okay, last big shape, a sphere in 3D. How do you build a sphere in 3D? With disks, the exact same way you build a cylinder in 3D. Only now, as you can see, the radius has to change a little bit too. In other words, the radius of my disks has to change as well, okay? I'm going to use the same approach I did before, the moment of inertia of the sphere. I'm still going to integrate over disks, and each disk about its center is 1/2 mr squared. dm in this case is the total mass divided by the total volume of a sphere, which is 4/3 pi r cubed. And then we multiply by the area of each disk, which is pi r squared, which I'm going to let vary. And then dz is the amount of thickness that the sphere has. So I'm integrating upward, okay? So what does that look like? If I plug in dm, then I will say something like, how do I express r in terms of z? That's the thing that you always have to figure out. So, okay, so this is just Pythagorean theorem. So r squared plus z squared equals big R squared. And so r squared is just this. So I'm going to get rid of r. I'm going to plug in what I just found for r, so that's here. And then also dm has an r in it as well, so I plug that in here. And what I'm left with, this is amazing. This 3D shape is really just a 1D integral. And so, okay, you can shake all that out. You can clean it up a little bit. And by the time you're done doing all that stuff, you'll end up with 2/5 mr squared. I encourage you to work that out for yourself. It's a standard result. You'll find it in most tables. But it's probably good to do on your own at least once. Okay, now, here we go. As promised, a composite 3D object with a void. We are going to try to avoid doing integrals as much as possible. We're just going to say, look, this composite object is really the moment of inertia of the cylinder plus the moment of inertia of the sphere plus the moment of inertia of the void. And so we're going to use parallel axis theorem. The moment of inertia of the cylinder about this axis is the moment of inertia about the cm plus mh of the cylinder squared. The moment of inertia of the sphere about its axis through its center plus its distance plus the moment of inertia of the void. Remember, the void has negative mass plus its distance. That's parallel axis theorem. Okay, and then if I punch in all of that stuff, then I have a 12th ml squared plus a quarter of the cylinder. So this takes care of the cylinder about its center of mass. This is the parallel axis theorem piece for the cylinder. This is the moment of inertia of the sphere through its center. This is the parallel axis theorem piece for the sphere. Whoops. Oh, yes. And this is the moment of inertia of the void through an axis through its center. And then this is the parallel axis theorem piece. You can pause the video and make sure I didn't screw up the geometry here, but you've got basically this whole distance to account for. There's not really much to do after this other than a whole bunch of algebra. What I will say is don't forget that the void has negative mass, so you'll want to treat that the way that we've treated it in the past, which is to say mass per unit volume times the volume of the void, and then don't forget you have a minus sign there. And then if you plug all this in, you will discover what the moment of inertia for this crazy, crazy object is. Okay, so the point I'm making is you don't need to do a brand new unique integral. What you want are a set of solid skills that you can use to reduce or break complicated shapes down into simpler shapes. And hopefully you will find this more useful than confusing.